Oh, okay, guys. This is what you get. Let me make sure that is focused enough. I think it is. Yeah, okay. Alright, so this is one absolute value is -0.8 inequalities. So we can catch up and be ready for tomorrow, Wednesday's lesson, which we will continue 1.8 tomorrow. Alright, so absolute value equations. So recall, this is the definition of absolute value. This definition is sometimes hard to understand. You're really going to need to understand it in calculus. But I just wanted to give it to you so you have a full set of notes. So the absolute value equals. So this absolute value symbol breaks off into two things. It will equal just x, the stuff that's on the inside, if the stuff on the inside is positive or 0. Okay? Or it'll equal negative x, that means the opposite of x. That's how we read that, the opposite of x. If the inside is negative, less than 0. Okay? So if it's positive or 0, it stays the same. If it's less than 0 or negative, it becomes the opposite of x, so it turns into a positive. Okay? That's the definition. Another definition, you can also think about it as the distance away from 0. And again, you can go left or right, right? So there's the negatives, positives, but distance is always measured as positive. Okay? Alright, so if we solve these, we need to think, okay, so a couple ways you can think about it. What makes have a true statement, like what can you plug in there and equal out absolute value equals 3? Okay, or think, what numbers have an absolute value equal to 3? So what numbers, their absolute value actually turned out to be 3? And you guys should be saying x can equal 3 if I plug in 3 there, or x can equal negative 3. So in general, two solutions, because both of these have a distance of 3 compared to 0. So those two solutions, if you check them in the original equation, make a true statement. Absolute value of 3 is 3. If you plug in negative 3, absolute value of negative 3 is 3. So they both check out. Okay? So this definition is, if you are positive, you stay the same, okay, or 0. If you're negative, you become the opposite. So you became the opposite. That's what that definition is saying. I'm just doing a lot of notes to review what you were supposed to learn in 1050. I know you might not have all that stuff in there. You don't have to check these, guys, but I was just showing you how it makes a true statement and why you have two solutions for these problems sometimes. Here, be careful. Again, you always want to do this think step. I talk about that think step in the quiz review. So think, what numbers have an absolute value equal to negative 2? So what can sit in here and equal negative 2? Well, anything that comes out of here is going to be a positive number, or it's going to be the number 0. Anytime you walk out of the absolute value bars, this number is going to be positive, or that number is going to be 0. So there's no positive number that equals negative 2, and 0 doesn't equal negative 2. So this is no solution. So you really want to do this think step so you are not screwing up and saying the answers are 2 and negative 2. No solution. No solution. Okay? Absolute values cannot equal negative numbers. Okay? Alright. So let's apply that to harder problems. I was just reminding you of the conceptual stuff. So in general, you want to get the absolute value by itself. So get absolute value by itself. So we're going to subtract 5. The absolute value of x minus 3 equals 4. So then you want to think, and I'm not writing all this out, but you want the stuff on the inside, so I call this stuff crap. You set the crap equal to 4 or negative 4. Okay, that's what you want. So x minus 3 equals 4, or x minus 3 equals negative 4. You want the stuff on the inside to turn into a 4, because then it'll make a true statement, or you want the stuff on the inside to turn into a negative 4, because this will be then a true statement. So you got to get the absolute value by itself first, then you can think. So if I add 3, you get x equals 7. If I add 3, I get x equals negative 1. Now be careful, a lot of people think, oh, you can't have a negative answer for absolute values. No. You can plug in negatives. You just can't get out negatives. So whatever you plug in is going to turn this into a positive. So you just can't get out negatives. You can plug in negatives, that's fine. You can't make them equal to a negative. That's the difference. You can plug in a negative, it can't equal a negative. Okay, so be careful of that. Two solutions. Alright, again, get the absolute value by itself, multiply both sides by negative 2. So that becomes positive 2, and now we can think 5 minus 3x equals 2, or 5 minus 3x equals negative 2. Or, yeah, equals negative 2. Sorry, I'm running out of room here. So, I'm going to solve this. So I'm going to subtract 5 from both sides and divide by negative 3, so I get 1. Subtract 5 from both sides, I get negative 7. Divided by negative 3, I get 7/3. So two solutions. So again, be careful. You could get, if it equals a negative, that's not possible, so you have no solution, or you can get more than one answer. One more, just so you know, very quickly. Lord. Come on, Sam, get it together. Call this A, B, C, D, E. Absolute value of 5 minus x over 2, I don't know, make it a little fancy, equals 0. So the absolute value is by itself, okay? It said I can't equal negatives. I can equal 0, but 0 isn't positive or negative, so you're not going to have two solutions here, you're only going to have one, okay? There's no negative 0, okay? It's not positive or negative, it's neutral. So you're going to have one solution, one solution. So if I clear fractions, multiply both sides by 2, I get 10 minus x equals 0, and then 10 equals x. I added the x to both sides, so x equals 10. Okay, so only one solution in that case, because there's no opposite of 0. Okay. Alright, so there's absolute value equations. That's the end of 1.5. Now we are going to do 1.8. Start 1.8. Absolute value inequalities. Okay. 1.8 is actually all inequalities, and then right now we're going to do absolute value inequalities. Okay, so we'll finish the rest of 1.8 tomorrow. Alright, absolute value inequalities. So this guy, I'm not going to show like everything you were supposed to learn in 1050 as far as like all of the think stuff. I'm just going to straight out go with the shortcuts that you should have learned by then in 1050, just because of time. Okay, so I'm actually going to go through just solving, okay, right away, immediate examples. So the directions will say solve, write in your answer in interval notation. Alright, so here's A. Let me find my example, my lovely people. So, here we go. Absolute value of x plus 4 is less than 6. Okay. Alright, so you need to think. Perhaps it has an absolute value less than 6. Okay, think. Okay, I'll do one example of the long 1050 thing you should learn. So here's my crab. Okay, that's the inside must be less than 6. So absolute value of crab is less than 6. So if you think on the number line, you need to compare it to the number 6, but you also need to compare it to negative 6 because it's an absolute value. So these are open circles because there's no equal sign. And if I want this stuff to turn out to be less than 6, so if I plug in 7 for my crab, okay, so absolute value of 7 is 7 less than 6? No, so it's not those numbers. If I plug in negative 7, absolute value of 7 is less than 6, 7 is less than 6, no, so it's not those numbers. So we don't want any of those numbers to turn out, or those guys. So this is just to set up your inequalities. And then if you pick a number here, pick 0, 0, absolute value of 0 is less than 6, 0 is less than 6, that works out. So this is what's going on. This, because it's in between, is an and statement. Okay, it's an and statement. It's a less than symbol. Look, that's a less. This is what one of my students taught me, how they remember. A less than symbol, it's an and statement. Okay, so when we break up these two inequalities, just like with equations, we break up two equations. Now we're going to break up two inequalities. you have the crap. Let's look at our stuff here. This direction, let me do some color coordinating here. This direction here, that is less than positive 6, so it stays the same. And then, and that's the word and comes in, and, less than. The crap on the inside, if you look, this shade is to the right, so in between, that's greater than negative 6. So what happens is, again, you can just remember the shortcut. It's an and statement. You keep it the same, and then you flip the sign and flip the sign. Okay, you should learn that from 1050. I'm just showing you with this think step or think graph of how it's set up and why. There's my think graph. It's the in between. Then you're just going to solve these. So actually I'm going to set up the right thing. So our crap is x plus 4 is less than 6, and x plus 4, I was putting crap again. Let me get my white out, guys. Where the heck is my white out? Come on, Sam, get it together. Okay, no white out. We'll survive. X plus 4 is greater than negative 6. So then you solve these. X is less than 2. X is greater than negative 10. This is interval notation, so when you graph this, so this answer graph should match this guy. It should go and it should be an in between. Okay, it should be in between like that. So let's see what happens. 2 is positive, it goes over here. Negative 10 goes over here. And if we graph these, so let me do my color coordinating. Okay, less than 2, that's all of these numbers. Okay. And greater than 10 is all of these numbers. But you only take an and statement, you only take where they intersect. So where do they intersect? In between, like these guys intersected in between. So this is the answer. Your graph is in the middle. Open circles because there's no equal sign. Negative 10 to 2. Soft brackets not included because they're not shaded in. That's your interval notation I'll be looking for. Okay. Alright, so there's, I'm not going to review that again. The ors will go out. We'll do an or right now. I'm just going to go straight to like breaking it up and going. Okay. Looking for my green. Alright, so I'll start on a new sheet of paper actually. Here's B. If I was in class I would have been flying a little bit more than this, but I'll take my time here. So for B, I have absolute value 2x minus 3 is greater than or equal to 1. So this is an or statement. So greater. So my other student, my same student told me, so greater than. You can see this as greater than. So then it's an or statement. That's how they were remembering this. The other one was less than, was the and statement. So you want, very quick, I'll do it. Think. Okay. 1, negative 1, these would be closed. So absolute value of, pick a number bigger than 1, 3, is that greater than or equal to 1? So this is my crap. 3 is greater than or equal to 1, so yes, no, yes. So it's going to be this way, and it's going to be this way. So this is an or statement. Okay. Again, if you check these numbers, they 5 is greater than or equal to 1, yes. 0 is not greater than or equal to 1, so it doesn't work. So this is an or statement. So we have our crap. 2x minus 3 is if you look at this pink one, okay, that is less than or equal to negative 1. That shade is less than or equal to. And if you look at this blue one, that shade is, oopsie, greater than or equal to 1. So this was the negative 1, this is the positive 1. So in each case, and or, they stay the same, and then they flip and flip. Okay, and don't forget to have your little or here. You must have or written. Okay, that tells you how your solution works. Alright, and then solve these. So 2x less than or equal to, add 3, you get 2. x is less than or equal to 1. 2x is greater than or equal to, add 3, you get 4. X is greater than or equal to 2. So when you graph these, 1, 2, these are both close because there's an equal sign. I'll do my blue shade. Greater than 2 is this way. Less than 1 is that way. Oh, look, you should get the same kind of graph. It's an OR statement. OR statements don't take intersections. They take everybody. They're actually not picky. So negative infinity to 1, hard bracket because it's included, union 2 to infinity. Those are all your solutions. Remember, infinities get soft brackets. Okay. So absolute value inequalities are very, very annoying. Okay. So you got to do a lot of thinking. Make sure you set them up correctly. Here's C. Negative absolute value 3x plus 2 is less than or equal to 5. Alright, so again, get the absolute value by itself. The first two examples, they would already by itself. So get absolute value isolated. So, excuse me, I'm going to divide both sides by negative 1. And when you divide an inequality by a negative or multiply an inequality by a negative, you got to flip the sign. So flip the sign, you get negative 5. Okay? So just recall, multiply or divide inequality by, so multiply or divide inequality by a negative number, flip sign of symbol, less than, greater than, whatever it is. Okay, just remind you. Alright, so now we got to think. Absolute value greater than or equal to negative 5. Okay, so in the last example with the equations with the negatives, that was a little weird, that they cannot equal negatives. But in this case, it's saying what can sit here and be greater than or equal to a negative number. Okay. Well, when you come out of an absolute value, what are you always? Positive or 0. And is a positive number greater than a negative number? Yes. Is 0 greater than a negative number? Yes. So all positives or 0 are greater than negative numbers. Okay, so this is all real numbers. Or inequality or interval notation. Bam. All positive zeros are greater than any negative. Okay. Any negative number. Now you might be thinking, what about that equal sign? Like, oh, you can't have a positive equal to a negative. For an or, the word or in math is very special. It says greater than or equal to. As long as one of these is satisfied, it's fine. They don't both have to be satisfied. So since the greater than makes a true statement, it's good. So you don't even have to worry about the equal sign. Okay? Alright, so that's greater than a negative number. That's all real numbers. Let's do the next one. A, B, C, D. Absolute value of 5 plus 3x plus 6 is less than 2. Again, isolate the absolute value, get it by itself. I'm going to minus 6 from both sides. Absolute value of 5 plus 3x is less than negative 4. So you got to think. Okay. When is the absolute value of crap less than negative 4? So again, this stuff is going to be, this crap is going to be positive or 0. Anytime you come out of absolute value, you're positive 0. When is a positive number less than a negative number? Never. Ever. Positive numbers is never less than a negative number. 0 is never less than a negative number. Okay? So this is no solution. So be careful with your inequalities, your absolute value inequalities. You can use no solution, you can use that symbol, you could use the empty set, whatever you want to use. You got to think about them. Okay? Is it possible? If it is possible, what are my situations? Okay? How many situations do I have to set up? So really, really be careful about your absolute value inequalities. One more thing let me say real quick that I did not mention, because people usually just have this in the wrong math. I know what you mean, but it's the wrong math. Very quickly, let me go back to here real quick. Here's my notes. When you set up your equations, So notice when I set up my equations, when you set up your equation, you no longer have absolute value on those individual guys. Because by definition, when you break it up, there's no more absolute value. Okay? Same thing with your inequalities. When you set up your inequalities, you no longer have absolute values on there. You just go and proceed solving like normal. So just make sure you have the right notation. Alright, so I'm going to upload this video. It's going on YouTube. I'll give you the link. Clearly you know that since you're listening to me right now. And then these notes will also be scanned in a PDF on Canvas. I hope I'm done. I hope I don't need to tell you anything else. Let me make sure before I stop this video. Alright, we're good to go, guys.